In this video, we're going to be looking at magnetic resonance imaging, and we're going to carry out one of the simplest imaging experiments possible on a very simple sample comprising these two tubes of water. Remember that the Larmor precession frequency of the nuclear spins depends upon the strength of the magnetic field. Now just imagine if we could make the magnetic field higher on the top tube and lower on the bottom tube. That would mean that the top tube would have a higher frequency and the bottom tube would have a lower frequency. And if we looked at the spectrum of that, we should see two signals at two different frequencies corresponding to the two tubes of water. Now imagine if we could make that magnetic field vary linearly along the axis where the two tubes are separated. In that case, we'd have a very simple relationship between frequency and position. In fact, our frequency axis would also be a position axis. How could we do that? Well, we have the gradient coils. These are the coils that are inside the probe of the Terra Nova apparatus. And these coils are able to produce a variation of the magnetic field along the vertical direction, varying along each of three orthogonal directions, along the X, Y, and Z direction. In this case, of course, we only need to have a variation of field along the Z axis, where we're going to separate those two tubes of water. So the idea is to use these gradient coils to produce the variation of magnetic field along the Z axis in combination with a spin echo experiment. We will see the spins come into phase and then back out of phase again under the influence of that magnetic field gradient. So now we're going to do the MRI experiment. First, I need to put the two tubes of water into the probe. And now I'll run the experiment. Prepolarizing pulse, and then the spin echo sequence under the influence of the gradient. And here we see the nuclear spins coming into phase, the centre of the echo, then going out of phase across in this time domain representation of the signal. What we have to do is to Fourier transform this echo signal in order to obtain the spectrum. And here it is in the right-hand panel. Indeed, we do see two peaks, one on the left, one on the right, corresponding to a lower frequency and a higher frequency, the tube at the bottom and the tube at the top. And of course, this frequency axis along here is simply a position axis. A position axis because of that simple relationship between frequency and position, which is created by the linear variation of magnetic field caused by the gradient coil. Of course, in magnetic resonance, we're very used to the idea of a Fourier relationship between time and frequency. But it turns out there's also a Fourier relationship between position or space and spatial frequency. And these ideas of spatial frequency turn out to be really important if we're to have a deeper understanding of MRI. In fact, these ideas are really essential if we want to understand the way in which MRI works in 2 or 3 dimensions. In the next video, we're going to be looking at MRI in higher dimensions and looking more deeply at some of these ideas around spatial frequency.